Welcome all to the week 6 live session of dissociation of quantum chemistry of atom and molecules. I am Arpuru Chaudhary, a PMRF from IT Bombay. Today we will discuss some of the numerical questions from Macquarie Simon's physical chemistry books on the quantum chemistry, some numerical problems, and uh, whoever is watching live, they can ask me direct question or something like that, and whoever is attending this session via YouTube or watching this video in YouTube, please comment on the video. If you have any doubt, we'll try to reach out to you. Okay, let's begin then. So these questions are from actually Macquarie Simon's physical chemistry book. You can see that. So the first question is actually a normal numerical problem. It is not. It is about the measurement theory, the mean value and other things. So the question says for a particle moving in a one-dimensional box, the mean value of x is a by 2, and the mean square deviation is psi x square is equal to a square. It is given by some expression which is written here. So we have to show that when n becomes very large, these values agree with the classical values, and the classical probability distribution is uniform, which is given by p of x dx is equal to a 1 by a dx, which is x is between 0 to a, and otherwise when x other values of x, it is 0, p of x is 0. Just particle in a box problem, and the classical probability distribution is given. So the mean value of x is given, and you need to calculate that if the mean square deviation is also given. So you need to see that when n becomes very large, if the classical and the quantum mechanical thing that is coming into similar picture or not. So let me tell you something that firstly, that this sigma x square, which is given by the mean square deviation, is actually given by this. We have solved few problems in last week also. One problem like this, where square of the mean value or the average value of x, and it is the average mean value of square of position. So now what is given? So this is given is the classical probability distribution is given. So and it is also given that sigma x square is equal to a square by 12 1 minus 6 by pi square n square. So when n becomes very large, that means n becoming infinity, what will be sigma x square? A square by 12, that 1 minus 6 by pi square infinity square. Am I, did I switch on my, did I unmute myself in my watching phone? No, actually I'm not. I'm very sorry. I hope, okay, no one has joined it. Okay, it's only me then. Problem. So now this will lead to a square by 1 to 1 minus 6 upon 6 by 6 into 0, right? Because 1 by infinity square, that is, this term is going to be 0. So you are going to get a square by 12 when your n is very large. So uh, then your uh, quantum mechanical mean square deviation is going to be a square by 12. And what about this classical? This is from quantum mechanics. Now classical picture is given, right? This is, so your classically your uh, probability distribution is given. So it is actually your a square is classically. I am now showing classically. that is your 0 to a 1 by a x square dx. This is given, right? So I am putting just x square there, and it is between 0 to a. So you know what will be the integral. This is cubed by 3, right? From a to 0, and it will give you a square by 3, right? And similarly for x, you will get classically 0 to a x dx, which is 1 by a upon x square by 2 a 0, which is a by 2. So obviously, so this will become, the square will become a square by 4. Now one thing, first you see that the mean value of x is a by 2, that we know from earlier, right? L by 2. But here from classically also we are getting that, but there is no n dependency on that, that you know earlier, right? But where the n dependency is there in the mean square deviation, right? So from quantum mechanical perspective, you got that when n is very large, which is near to infinity, the a square, this becomes a square by 12. Now classically what we are getting, classically you are going to get sigma x square, same, we need to put that formula, right? So this will get a square by 3 minus a square by 4, which is nothing but your a square by 12. 4 here, 3 here, 4 a square minus 3 a square by 12, which is square by 12. So it's actually these two terms are now equal. So that is what they wanted to show us. They show that the when n becomes very large, this value agrees with the classical value. So classical value is this. And anyway, both the values are now same. So when n becomes very large, both the value becomes equal. Okay. Now I'm recording my session. Yes, it is recording. So as one has joined it, so you can watch this thing online. So the next question is 4.17 is referring to the table point 4.1, where it is there in the Macquarie book. So I have just pasted it here. That angular momentum. So different angular momentum was given like this. Okay, show that the commutator relationship, that Lx Ly is equal to IH cut Lz, Ly Lz is equal to IH cut Lx, and Lz when operating with Lx it will be IH cut Ly. Do you see a pattern here to help remember this commutation relationship? What do these expressions share about the ability to measure the components of angular momentum simultaneously? So let us first do this, at least one Lx and Ly. We will get the gist of this. So first, Lx is the angular momentum along the x-axis. Ly is the angular momentum along y-axis, and Lz is the angular momentum along z-axis. Now you know, so this is the angular momentum for a space. When the thing is there in a rotational motion or something like that, right? In a spherical coordinate. But when you, for linear momentum, so that's your angular momentum, and linear momentum, you know already the operators, right? That, let me just give the cap sign so you will remember this. Okay, so I'll not bother about this. Okay. Stay the call. Okay. Okay. Now don't have to explicitly write that. The thing that came from, how did we get these things? So you can remember like this way, that Lx, Ly, Lz, okay, and you remember x, y, z, px, py, pz. from here actually you can do this thing. If you think about Lx, you need to take this determinant. Then your Lx will become ypz minus zpy. I am not writing the cap right now. What will be for the Ly? Ly is zpx minus xpz. Remember about the signs. See, we are getting back this. So I'm just writing it how to remember it in a simple fashion. And most of the time it will be given in the question, so you don't have to remember this. But if you have to do, you can use this process, right? Now you know what px, py, pz are, right? Px is minus ih cut um, ih cut del by del x. Py, this is linear momentum, right? Operators. Minus ih cut del by del y pz minus ih cut del by del z. You just need to put these values here to get this kind of expression. Okay. Now I am going back to the mathematical numerical problem that is given here. So the question is, we need to evaluate the commutator relationship of Lx and Ly. If they commute or not. Clearly we have to show this so they don't commute, but what is the expression for this? So this is nothing but Lx Ly plus Ly, not plus, so I have made one mistake here. So this will be minus Ly Lx. Okay. Now when it is operating on f, one function, it will be something like this, right? So I will write the thing here. So as they are all linear operators, remember that the quantum mechanical operators are Hermitian and linear. So linear means it will come here Lx Ly work on f minus Ly Lx operating on f. So Lx will first operate on f, then Ly will operate. Similarly, Ly will operate on first on f, then Ly. So we'll just write it in this term. So we'll write individually. Okay. Then we go to the next page. So first we'll check what is the value of this. So Lx you know that is minus ih cut. Lx is y pz z into y pz del y del z, right? Into minus ih cut Acha, I have missed one portion. This is minus of minus ih cut z del y. Okay. Then it is starting the second for Ly. Ly is z del y del x minus of ih cut x del y del z, and it is operating on it. First this will operate on this and then it will operate on, but take sphere of the IH and all. So I can take out IH cut outside once, IH cut square actually, not square, right? No, IH cut outside, so it will become y del by del z minus z del by del y, then z del x minus x del y del z, right? And the whole thing will operate on x. Okay, so instead of this, what I can write, let me write step by step, or else I may make mistake. I'll just multiply this thing as it is. So when, so so y, so so first I'll just erase one thing and replace this f here. See, I'm just taking writing f here because this will work on f first, right? So y del by del z on z del f by del x, okay, as well as x del f by del z, then z del y del y will work on z del f by del x minus x del f by del z. So when y del by del z work on z, so you remember that this kind of so when it is uv kind of thing, right? D of d by dx of u and v when u be a function of x, so then you got u v dash plus vu dash. So it is something like y, so first it will work on z and del f by del x will remain constant, del f by del x, and del z by del z is, I'll just write it once so that everyone can follow, and the next will be plus y z del z of del by del z of del f by del x. Now second, there is x is there, so x is not a function of z, right? They are all also on the orthogonal, right? So x will come outside, del by del z on del f by del z. Now next, similarly there is no function of y, so this is the whole term. Let me put one thing, z. So this will look like z square, okay, z square del by del y into del f by del x, as there is nothing, right? The function is f is function of all x, y, z. So I can't take it as constant and make del y del by del y of del f by del x is 0, right? So that is not a constant. Now I will get some plus here, z, and it will be zx because x, and so this is not a function of y, so it will be del of del y del f of del z. So, any participant here, I guess? No? Well, fun. Now we'll simplify it even more. So y del f by del x, this will give us 1 plus yz del square f del z del x minus yx del square f del z square minus z square del square f del y del x plus zx del square f del y del z. So we need to get the same thing for Ly, Lx operating on f, right? Let's see what we will get. So we'll get something. I will start from the second one, second step. I squared, let me take common. Now we'll take the different, so we can replace z del by del x minus x del by del z, right, into y del by del z operating on f minus z del f by del y. This what we will get from here, I cut. Now what will get z or z del by del x. So y will come out. We get del square of f del x del z. So I am jumping a few steps because I have shown it explicitly in this case. I hope you can understand. So now the second is z square. I am taking this and z square del square f del x del y. Now the second and third minus x y del square f del z square. And what about the third term? The last two. So first of all, it is plus minus minus plus. Then x del y del z operating on z as well as del f by del y. So again x z del square f by del z del y and then plus x del f by del y, because now del z by del z again this become 1. Let's see what do we get here. Not that, but let us take Lx Ly, what we wanted to get, operating commutator operating on f, and Lx Ly on f minus Ly Lx on f. That is, let us take minus I each common for both of these. We'll put these values. So here we got y del f by del x. I'll just write down these terms again. Yz del square f by del z del x minus yx del square f by del z square minus z square del square f by del y del x plus zx del square a by del y del z. So this is done. Now I have to take this part, but it's minus. So minus zy del square f, but del x del z. Then plus, because minus of minus plus z square del square f by del x del y plus xy del square f by del z square, and then minus xg del square f by del z del y minus x del f by del y. So there are 10 terms are there, 5 from each. Let's see. I guess some of the terms are going to cut out. So let us see yz del square f by del g del x. Yz here see zy yz are same del 2 by del x del z. These are same plus and minus. So they are going to cut. I'm just going to use them. I'm just going to use a different paint color. So this and this cut. Now with another color, maybe black, yx del 2f by del z square del 2f by del z square. See xy yx. So these are same. So these will get cut. Then maybe with another color, z square del 2f by del y del x. So these two are going to cut. Now as you can see, the last one, that zx del 2f by del y del z, these are going to cut. But these two terms are going to remain as it is. So we'll write down what they are. So what we got is that Lx, Ly operating commutator operating on F, we got minus IH cut y del by del x minus x del by del y, which is nothing but so so am I missing one IH anywhere? Yes. See, here one IH is common from these two, and here one IH is common from there, but that is multiplicative. So I should have write IH square. And similarly for this also. I hope you understand why I did the square, because one will take common from here and one will take common, that would get multiplied. So to keep it outside, it will stay like that. And here it is also square. So what we got is minus IH cut will take 1. Okay. And it will be again minus IH cut second bracket y del by del x minus x del by del y, second bracket close, third bracket close, and then f, which is nothing but you say minus IH cut into, this is nothing but LZ operator, right? So what you got there is minus IH cut Z. Is it so? So there should be no plus IH cut. Have I done any mistake? Let me check. Where have I done the mistake? Minus IH cut Y del by del Z. Have I written it correctly? Minus IH cut. Right? Okay. IH cut square, IH cut square. I have to multiply it by minus H. I have done a mistake somewhere. Okay. See. Here y del by del x. What is LZ? LZ is, if you can see, x del by del y minus y by del x. So LZ is minus IH cut x del by del y minus y del by del x. If one need to write it in, so minus, if we can include here IH, will become y. So minus LZ, so let me write it like this, minus IH cut y del by del x minus x del by del y. So this is what we got, minus IH cut y del by del x. So not LZ but minus LZ we got. So it becomes plus IH cut LZ. So what we got is, I'll write it in here, like this, Lx comma Ly. The eigenvalue of this commutator is IH cut LZ. I'll just highlight this part. Okay. Similarly, one can show that LYLZ will be IH cut LX, right? But LZLY will be minus IHLY. So this going in a circle. So then LZLX will be IH cut LY. So this is your homework. You can solve it. These two. Mark it in different highlighters. So these two you can try at home. So it will be similar. Try to solve it for both of them. Okay. So I will just, next question, I'll just go back and we'll see the pattern. So that's what I was saying, that yes, we can see a pattern, right, which can help us remember the commutation relationships, because Lx Ly will give it to you IH cut LZ, Ly LZ will give it to you Lx, and LZ Ly will go to IH cut Ly. Firstly, then do you see a pattern here to remember this commutation relationship? What do these expressions say about the ability to measure the components of angular momentum simultaneously? Firstly, that when they commute, they can be measured simultaneously. You remember that for where is my pen? Okay. When x and px they did not commute right for a particle in a box. That's why x and px cannot be measured simultaneously. That's what lead to your Heisenberg uncertainty principle, right? So when these two cannot be measured, when two operators can't be measured simultaneously, their operators don't commute, or vice versa. When they don't commute, you can't measure them simultaneously. So here you can see that Lx, Ly, commutation in relationship of that and the others, Ly, Lz and Lz, Lx, they don't really commute, means they don't really give the commutator value as 0. That is why they can't be measured simultaneously. So this is a very important statement, that Lx, Ly, Lz, the angular momentum along x, y, z direction cannot be measured simultaneously. Okay, but next question is that define L square is given, defined by L x square plus Lz square plus Ly square. So we have to show that the L square commute with each of the components separately. And again, if they commute, that means L square and L. So let us first do it Lx, L square with Lx, right? On one of the component. And next I can give you homework, right? So we are going to see if Lx and L square they commute or not. What is the value? Okay. So L square is given. L square is L x square plus Ly square plus Lz square. Now, so this become Lx square plus Ly square plus Lz square contrary Lx. Now it will lead to Lx square Lx, right? It is something like this, as they are all linear operators. These are very interesting. So you see Lx square Lx is nothing but Lx square Lx minus Lx Lx square, right? So as they are all same, you will see that it is going to be 0. So you don't have, at least you don't have to worry about this. What about Ly square Lx? Let's look different than the previous one, right? X minus Lx Ly square. Now see, we have to manipulate it a little. First term, let us keep as it is. Then let us take like Lx, Ly, Ly. I have just broken down L square, Ly square into both. You remember what we got earlier for Lx, Ly? commutator, we got IH cut LZ, right? Similarly, what is that? LX LY minus LY LX IH cut LZ. And if we can replace Lx by Ly, this value if we need to replace, we need to replace it by IH cut Lz plus Ly Lx. We'll just replace this value here, Ly square Lx minus IH cut Lz plus Ly Ly Lx, and it is multiplied, right, multiplied by Ly. We can't forget it. Okay. So this will lead to us L square y Lx minus IH cut Lz Ly. So you can't write it Ly Lz because it is right multiplied by Ly. You need to multiply it right side. Similarly for this also, Ly Lx, and I have to write Ly here. I can't write L square Lx right now, and not like that. I have to write it like this. Similarly, what will happen to Lz square Lx, the third part, Lz square will do a similar thing here also. This is equals to, we will keep this part as it is like the previous manipulation. Here it is Lx Lz. I will just put Lz square as Lz into Lz. So similarly here I will write Lz square Lx. Now what is Lx Lz? Do we have something? Remember, we know Lz Lx as IH cut Ly. So Lx Lz will be negative of that, and we will get minus IH cut Ly. From there we can write that Lx Lz, I am forgetting the cap somewhere and I am writing it somewhere. So Lx Lz, that is actually your IH cut Ly minus of that and plus Lz Lx. I hope you got it, what I am trying to say. Minus IH cut Ly plus Lz Lx, which is right multiplied by Lz. And the whole thing is Lz square Lx minus plus IH cut Ly Lz minus Lz Lx Lz. Again, these two I cannot write it as Lg square Lx. So when I put all the things, now I am writing it again, that what is L square by Lx. So we first got this as 0, that is x square Lx commutation. Now the second part I will write it whole L square Lx Ly square, sorry, minus IH cut Lz Ly plus Ly Lx Ly now plus Lg square, this part now I am going to write this part, that is Lg square Lx plus IH cut Ly Lg minus Lg Lx Lg. Okay, so let's see what we can have, what we can cut. First let me take common of IH, okay, and is minus of IH, which is you get Lg Ly, and we have it here minus common, so we get Ly Lg. Okay, what else we have? If we take common between these two, if we take Ly common at the left hand side, we will get, bracket Ly Lx, and from here we will get Lx Ly. I have done a mistake here. See, minus of this thing should lead to minus and minus here, right? So we need to be very careful about this mistake. I'm very sorry for this. Again, minus there, so minus here, and eventually here, minus, minus here, and again we can take, when we will take between these two, we can take Lg as outside, and we'll get Lg Lx Glx minus Lx minus Lx Lg. Okay, so we'll simplify in the next page. L square Lx, we got minus IH cut, so see Lg Ly minus Ly Lg, so this gives us minus IH Lg commutator Ly, this is the shape, right? Then next, which we have common Ly, take common at the left hand side, we will get Ly Lx minus Lx Ly, right here. So it is Ly comma Lx. Here we got Ly comma Lx. Now next we got Lg Lx and Lx Lg. So Lg comma Lx. LG comma LX. These are all commutators, not third brackets. Okay. So here we got minus IH cut multiplied by LG LY. We know LY LG we know, right? That is IH cut LX, right? So minus of that will be minus IH cut LX. Check the Google Meet once. As no one is here, that's why. So now see Ly and Lx. We know Lx and Ly. This relationship is known, which is IH cut LZ, right? So we have solved it a few moments back. So again, we have to take reverse of that. So here we will get Ly into minus IH cut LZ. The third one, we know that Lx Lz operators will get IH cut Ly. No, I have made a mistake here. So Lx Lz Lz Lx is that. So opposite of that Lz here it is fine. So Lz here we will get only IH cut Ly. Let's see what we have it here. So minus IH square minus IH cut square, which will lead to right now I will not solve it. I will just put it like that. Lx square of that. I hope I am doing it correctly. Then we have the other ones. So this will lead to minus IH cut Ly Lz plus IH cut Lz Ly. Okay. So minus I square. Okay, this is minus I into minus I, which is plus I square. That is minus 1. So minus H cut square. I don't know why I have taken this much time to do this. But anyway, Lx minus if I am going to take this common again, minus H cut. So what I was going to get Ly Lz, take this minus Lz Ly. Okay. So again see we are going to get another commutator relationship. So actually this is just the calculation, we just need to do the calculation with concentration because it can come, some erroneous value may come, but you have to do this with concentration. H cut Ly Lz and Lz Ly is nothing but Ly Lz commutator, right? And which is nothing but Ly Lz I have written here that Ly Lz is H cut Lx. So minus H cut square Lx minus IH cut into IH cut L, right? Let's see what we have it here, minus H cut square Lx and here minus I square which is plus now become plus 1 because it is minus I square h cut square Lx. So again, so we are going to get a 0, right? So after all of this calculation, tedious calculation I would say, and manipulation was there, manipulation, mathematical manipulation, we are going to get this as 0, which is very important result. The commutator relationship between the total angular momentum, square of the total angular momentum, and I would not say total angular momentum, the square of the angular momentum and one of the component along the x-axis Lx is 0. Let me highlight this. So from here we can see the commutation relationship between these two are 0, right? So they commute. So again, what I said earlier, that when both of them are going to commute, then you are going to see that they can be measured simultaneously, right? So which was not true for individual Lx and Ly, but here it is true. So similarly, you can show that L square Ly, this component, the angular momentum, square of angular momentum and Ly is also 0, and L square Lz, the angular momentum along z axis, this is also 0. So the main funda is that the square of the angular momentum and each of the component of the x, y, z, a angular momentum is going to be 0, and you can measure them simultaneously, the L square and Lx, L square and Ly, L square and Lz. You can't measure Lx, Ly, Lz simultaneously. So please try to solve for these two. So if you can try this thing at by yourself at home, this might be very beneficial for you to understand the calculation what I have done, and also see when you do it yourself multiple times, then you will be confident enough to solve it anywhere, right? So that is the purpose of this session, just to let you understand what are the how to do this. I have solved for one, you can do these two, right? Okay. So so these are for these questions, that one that we have understood that Lx, Ly, Lz, those commutation relationship, how to do that, and uh, that, and defining the second one. And now let us solve some question from maybe the rigid rotor problem. And this rigid rotor problem is actually is going to helpful in your molecular spectroscopy course, specifically in the rotational spectroscopy, right? Where uh, the similar approximation are taken, and from the solution of the Schrodinger wave function, you already know what is your energy and other things. I'll just write down one or two things here. So in the infrared spectrum of uh, H79Br, which is one isotope of Br is there, so which is 79, there is an intense line at 2630 centimeter inwards. We have to calculate the force constant of H79Br, one H79Br, and the period of vibration of that. Did you miss any question? No, right? Okay. Achha, we have some questions I guess here. Okay. Similar questions are going to come here. Far infrared spectrum. This is actually your rotational spectroscopy questions, and these are actually your um, vibrational spectroscopy, or you can say IR spectroscopy questions. So I hope you remember for this actually. So this is not from your rigid rotor problem, but from your harmonic oscillator. And when we so we also know for the first, so I'll show you one thing. So you already know, right, that the frequency of oscillation mu is 1 by 2 pi root k by mu. Mu is your reduced mass and k is your force constant. So see, from the question itself I am seeing that your nu bar, or it is also known as wave number, or you can say energy also, you can say energy in centimeter inverse. So this has been given. So you need to calculate force constant. So you need to remember that which formula to use, right, from here. So the formula is frequency is this, and one can, so these will come as hertz, right, or second inverse. So if you go to wave number scale, so your nu bar, so what is the relationship between nu and nu bar? See, you know energy is h nu, and this is also h c nu, right? So you can see your nu is c nu bar. So nu bar is nu by c. I just have to, I will just do 2 pi c k by mu. This will come in centimeter inverse unit, right? I have divided um, mu, which is in Hertz unit, second inverse, by centimeter uh, centimeter second inverse. So eventually second inverse gone, and your centimeter becomes my in denominator it was centimeter, so it will become centimeter inverse. So from here, what is the force constant? Force constant is 2 pi c nu bar, a square of that into your reduced mass, right? So let us calculate one by one. So all the other things are given. Constant 2 pi c, you know, nu bar is given, and mu we have to calculate. Mu is the reduced mass. So that is actually your uh, mass of H into mass of Br by mass of hydrogen plus mass of this, coming from that 1 by mu is 1 by m h plus 1 by m of Br, right? This is coming from there. So you know this is, let us take it an AMU unit, huh? 1 into 79. I am not going to too far, right? AMU, actually AMU square, AMU into AMU divided by 1 plus 79 is in AMU. So you got 79 by 80 AMU. AMU is nothing but atomic mass unit. And one atomic mass unit is in kilogram 1.66 into 10 to the power minus 27 kg, what I remember. Okay, I may be wrong. Let us see. Huh? I think I'm correct. 10 to the minus 27 kg. I should not confuse you. So let us see how much we got. Let me use my calculator, phone calculator. So we got 79 divided by 80 into 1.66, which is nothing but 1.64. Let me take it axiomatically into 10 to the power minus 27 kgs. Okay. So my force constant will be 2 into 3.14, 2 pi. C is 3 into 10 to the power C. I can take it in meter as well as centimeter, but I know that here already it is 2630, which is my wave number, that is already there in centimeter inverse. So I will try to take it in centimeter unit, centimeter second inverse, so that I can get rid of this thing easily. Or you can do whatever you want, but then your calculation will become a little tedious. So anyway, 2 into pi into c into your new bar, square of that, and here is your 1.654 mu, right? You reduce mass 10 to the 7 kgs. So what do we have it here? Centimeter inverse centimeter gone. So what we have, let me multiply also with the rest of the thing, into 2 into 3.14 into 3 into 2630 and square of that into 10 to the power 20 into 10 to the power minus 20, which in turn becomes 402.456 kg second minus 2. Don't forget the unit. Huh? So let's see what this unit is. So it is a force constant, right? Force constant, you know, force constant. So how can we write it? What are the other units of it? Um, you know this formula, right? That F is equal to Kx. It could be minus or plus. Let us not think about that. Let us take the mod. So force unit is Newton, right? And your K is something, and X is if it is SI. So your SI unit of this should be Newton meter inverse, right? But we got something kg into second minus 2. Can we convert it to that? Of course. So what we need to do is we need to multiply it with meter square. Okay. Then obviously meter minus 2. So it will become 402.456 kg meter square. Actually I could have taken meter 1. Kg meter second minus 2 into meter inverse. So this is nothing but your Newton, because you know your Newton is force, right? Force is mass into acceleration, which is kg meter second minus 2, right? Acceleration unit. This is nothing but Newton, so you got 402.456 Newton meter inverse. So my request to you guys is that don't directly write Newton meter inverse without seeing the units. Sometimes what happens is some units are given which is not exactly you can multiply and got. Sometimes you need to multiply with some constant terms. Okay, so then you can see we have made one mistake, but it's better to go step by step like this. I hope that is clear. So let us solve the next question, 5.14, which is of the uh, same order, which is your the force constant is given now. You need to calculate the fundamental vibration frequency and the 0 point energy. Okay, so now this is not HBr, which is 79. Here it is BRBR 7979. Okay, so mu is changed 5.14, right? So your BR is changed. So mu is changed. Mu is now 79 into 79 by 79 plus 79 AMU into 1.66 into 10 to the power minus 27 kilogram AMU minus 1. So I'll just calculate in my calculator, which is 79. So I'm getting 65.57 minus 27 kg. Okay. K is given force constant, which is 240 Newton meter inverse. I need to get the fundamental vibration frequency now. We know the relation 1 by 2 pi over K by mu. So 1 by 2 into 3.14 root over K is 40 Newton meter inverse divided by 65.57 into 10 to the power minus 27 kg. So you already seen that your Newton meter inverse is actually kg second minus 2, right? So you can write it like that also, that it is kg second minus 2, which in turn kg will take apart. You will get 2 into 3.14, 240 by 65.57 into 10 to the power 27. I just took it in the numerator, and second minus 2 root over of that, it would come second inverse, which is known as hertz, unit of frequency, right? So I'll just calculate this thing, 1 divided by 2. I'm getting a huge value. 1, 2, 3. So I can also write it in terms of nu bar, which nu by c, to make it so let me write. This calculation is 9.63334 actually into 10 to the power 12 second inverse. Okay, so this is the frequency. Or if you wanted to know the wave number, then it would have been nu bar equals to 321.14 centimeter inverse. Now if one wants to calculate the 0 point energy, so the 0 point energy is what? Half h nu or half hc nu bar, right? 0 point energy, no harmonic oscillator, so half into 6.626 into 10 to the power minus 34 joules second into 3 into 10 to the power. So C nu is nothing but your that value, right? Or 9.634 into 10 to the 12 second inverse. Second inverse 1, so it will be in terms of joules. To 6.626 into 10 to the power minus 34 divided by 2. It is 3.19 into 10 to the power minus 21 joules, which is very, very small, right? So this is the answer. I hope you guys are getting it. Let me check if anyone is there in the Google Meet. Okay. Okay, we have a few more minutes, 40 minutes. We'll solve some more questions. Okay. So explicitly for a harmonic oscillator that psi naught x is orthogonal to psi 1x, psi 2x and psi 3x, and that psi 1x is orthogonal to psi 2x, psi 2 and psi 3x. So the table 5.3 actually I have posted it here, that what are the wave functions that can be there, and here I have mentioned very important standard integral what one can follow. So if you see here, so for orthogonal relationship, you know what you need to do, that for if it is orthogonal to psi 0 is orthogonal to psi 1 or not, you need to integrate it for from the boundary. For harmonic oscillator is minus infinity to plus infinity, right? You need to integrate psi naught x with psi 1x dx. If it is orthogonal, then it will be 0. So we expect zero and another is, so these are the things we need to prove. So I'm showing you that we need to do a few calculations for integration of this kind. And the last psi 1 star psi 2x dx and minus infinity plus infinity psi 1 star x psi 3x dx 0. So first let me show you one thing. Can we all agree that integration of an odd function in a symmetrical boundary or limit is 0. What I mean to say, suppose x is an odd function, right? Suppose your f of x is x. How will you draw it? This is x, this is your f of x, and this is x. Right? So if you are going to, so this is an odd function. So what is the area under the curve between, so this is minus 5, this is plus 5, right? So area under the curve is this, right? Area under the curve. So if you see within a symmetrical uh, limit, the area under the curve is 0, which means the integration of this function within this symmetrical limit is 0. Because see, this part, this is going to give me a positive something, right? And this is going to give me a negative of exact magnitude but negative in sign. Is it true for all odd functions? Let us take. So you remember that um, sin x is an odd function. Let us plot that. X plus x minus, at x is 0, this is 0, pi by 2, it is 1, then pi, it is 0, then again 3 pi by 2, it is minus 1, and then at 2 pi, it is 0. I'm just drawing up to this part. And what about minus pi by 2? Minus pi by 2, it is minus 1. What about minus 1, right? And then again at minus pi, it is 0. And then again it will increase, and then it will increase. So apart from my poor artistic skill, you can understand this is really very poor. So what I'm trying to say, the area under the curve, if you see right now, from this is pi by 2, this is plus 2 pi, right? This is minus 2 pi. You can take any limit, right? But symmetrical. If it is, suppose it is pi, it is minus pi, right? You have to take it plus pi. That is what I'm trying to say. If you now integrate the area under the curve, you are going to, for this part you are going to get negative, right? Minus pi to pi, and here also you are going to get the same value, right? What I am trying to say, you got it. For this part you are also getting 0, right? Because this is same value will come but with a different area under the curve, total area under the curve. Now what about when we go to minus 2 pi, then also it is going to give me some positive thing, and here I am also getting some negative thing. So eventually all is going to be 0, right? So what my idea or what I am trying to say is that that integration of the area under the curve, I'm just going to highlight this. That the integration of an odd function, and this is true for all odd functions, is in a symmetrical boundary is going to be 0. Okay, this is what I am trying to say. So this will make our life a lot easier. See, we can do integration, right? Because I have given you some standard integral also, you can perform the experiment along integration. But why to do that if you have you're going to get it easier? So see, your psi star 0, sorry, x 0, psi 1 x. What is that? It is, so forget about the x part, a constant part. It is going to be x e to the power minus alpha x square by 2. Actually it is going to be minus alpha x square. But as x is there, so this is actually an odd function. Okay. So integration of this from a symmetrical limit minus infinity to plus infinity is going to be 0. What about psi 0 star x psi 2 x? You will see here it is x square. So this is actually even. Okay, even function. What is an odd function? Odd function is your f of x minus x is minus f of x. Then it is an odd function. Okay. Now what about 0 star means the complex conjugate obviously psi 0 psi 3x. You will see this is also an odd function because x cube is there. So this is also going to be 0. So this we are using let us write I. So following I, this is 0. What about psi 1 star x psi 2x is, wait a bit. Hello, I'm in class. I'll talk to you later. I'm in class. I'll talk to you later. Would you like to join? Hello. Okay. Sorry for that. So psi 1x, psi 2x. What is this? Is this the multiplication is odd or even? You are going to see that psi 1 and psi 2, so that is going to generate some, so if there is x e to the power minus x square, so this part e to the power minus alpha x square, this is always going to be even. That is an you remember Gaussian functions, right? Gaussian functions are symmetric, or you can say they are even. But the polynomial what we are talking about, see, the polynomial will make it odd function. It x cube term is going to be there. So when you change the x to minus x, your this is going to be odd. So this is also going to be odd. So that also you can prove from I, right? So these, number one, you can prove it from I. These you can prove it from I. This you can prove it from I. I means the ith equation or something like that. That is not a proper equation but a note, right? So what are we left with? So you can do explicit integration of that using uh, these also. What about um, what about the rest of the argument, which is those are even, like psi 1 star x psi 3 x. This is again even, right? Because x into x cube will be x to the power 4 and x into x will be x square, so it will be a even function again. So for these two we need to do calculation. Okay, so we'll do that. So for the first, let me write it a, we need to show that it is minus infinity to plus infinity psi 0 star psi 2 d. We need to show this. We need to show this. And what else we need to show? That minus infinity to plus infinity psi 1 star psi 3x dx is also below. And we have already shown this, right? These three. So we are going to need this uh, standard integral, but let me first start with the easier one, psi 0. Psi 0 is alpha by pi to the power 1 by 4. So as their even function, so we can also write it like 2 into 0 to infinity, right? Because minus infinity to 0 and 0 to infinity, as their even function, even if I take it minus x, so it will become plus x, right? So that is one way of saying. So if it is an even function, let me give you an example of even function, maybe x square, right? So I'll just do one for let me not let me just go with flow. Okay. So this is going to be what I was trying to say. Suppose your f of x is um, what can you say, cos x, right? So how does your cos x look like? Minus x. So it starts from here, right? Just draw a few. Oh, what is this boundary? Just change my color as I have done earlier. So this is 0, that it is 1, then pi by 2, right, and where it is 0. So this is pi by 2, this is minus pi by 2, right, these points. And this is again pi, this is minus pi, and this is plus pi. So if you check the area under the curve, this between pi by 2 and minus pi by 2, the magnitude is actually same and the sign is also same, which is twice of that. And again, if you increase your boundary to minus pi to plus pi instead of minus pi by 2 plus pi by 2, you are going to see that see for this you may get total of 0, but that is not the point. The point is when you take a symmetrical limit, suppose like for minus pi by 2 to pi by 2, right? So there you see the area under the curve is twice of the one side. Now similarly, I think I have made mistake. Here it is minus pi by 2, 0. Here it is. I've done one mistake. Here it is minus pi. Here it is plus pi. Here it is 3 pi by 2. Here it is minus 3 pi by 2. Okay. So when you take this kind of thing, what I'm trying to say, the area under the curve of an even function between symmetrical limit or boundary is actually twice of one part, one side. I'm going to show you what I'm trying to say here. You know, so here what I'm trying to say, minus infinity to infinity is actually for a even function is twice into 0 to infinity. So that is 0 star x I 2x. Okay. I'm just going to prove that, so I'm doing equals to, which is 2 into, and now I'm going to put the values. Let me first write down the constant alpha by pi to the power 1 4. Size 0 star, there is no such, I guess, I term is there, and let me harmonic oscillator, there is no there any 4 alpha and the rest of the 4 alpha q by pi. 0 to infinity. Now this part is e to the power minus alpha x square by 2 into, I have made one mistake. Side 2 is alpha by 4. Alpha by 4 by to the power 1 by 4 e to the minus alpha x square by 2 into 2 into alpha x square minus 1. So alpha x square minus 1 into e to the minus alpha x square by 2. We are not going to require that integration, because this is going to be, or we may, so 2 into alpha square by 4 pi square 0 to infinity 2 alpha x square minus 1 e to the power actually minus alpha x square dx, which is nothing but again 2 into alpha by 2 pi to the power 1 0 to infinity 2 alpha x square e to the power minus alpha x square dx, and another part would be 2 into alpha by 2 pi to the power half 0 to infinity e to the power minus alpha x square dx. Okay, so we are going to use some standard integral for that, which I have mentioned it here, I guess. Here, so see, I'll write it here once again. 0 to infinity let it now I think helpful. Okay, now see, your n is 2 for the first part. Okay, so and n is also even, so we are going to use the first one. So I have mentioned earlier also that earlier in the last class that your double factorial means that n minus 1, n minus 3, n minus 5, like this. Okay, what do I mean by that? That suppose 5 double factorial is 5 into 3 into 1, something like this. Okay, so 2 into alpha by 2 pi to the power half 0 to infinity, what we are going to get here, 2 alpha is constant into x square. Now integration of 0 to infinity x square minus alpha x square, so I will put that 2 minus 1, which is 1, 1 double factorial is 1, divided by 2 by 2 into n is 2 here, so but I will write it explicitly once at least, into a to the power 2 by 2 into root over pi by a. What about the next part? 2 into alpha 2 pi half, here n is 0. Okay, so you can say that it will be minus 1 double factorial, which is actually 1, divided by 2 into 0 by 2, 0 means 1 into a to the power 0 into root over pi by a. So I'll forgot, but I'll just check if minus 1 double factorial is how much. Just let us first solve it for this part. So what we are getting is 2 into, when we write in terms of this, alpha by 2 pi. This is common, I guess. So I'll take this thing at common. 2 alpha. 1 double factorial will be 1. 1 divided by 2 to the power 2 is 4 a, okay, minus, this is common, minus 1 double factorial, I guess it is going to be, I hope it is going to be 1. I'm not sure about this. 2 root over, acha, pi, root over pi by a is also common, so I'll just write it pi by a. Acha. So I took the values of alpha from here and to also see that what they mean by alpha. Alpha is Macquarie-Simons, they have written. Is anyone there? Just check in harmonic oscillator what they meant by alpha. Well, somewhere they have like this mentioned what is alpha. This is the solution. No, and just what is the value? The relationship between alpha and a could be. Am I making any? Okay. I am making a mistake, right? This is a very silly mistake. I'm very sorry, because instead of a, we need to take it alpha, right? Very bad. This is actually alpha, and this is alpha. So alpha 1. Okay, so 2 by 2, right? So 1 by 2 minus 1 by 2 is 0, so it is ultimately going to be 0. So what we got, that I0 star x I2 x dx is 0. Minus z plus infinity. So anyway, we proved it earlier also that the other part are 0, but here also we have proved again. What about the second thing? Psi1x and Psi2x, we will do it here. by 3x dx minus infinity plus infinity, which will be equals to, it is 1 4 alpha cube by 4 pi. 4 alpha cube by pi to the power 1 by 4, right, into whatever 3 alpha cube by 9 pi. Zero to infinity. Now x e to the power minus alpha x square into 2 alpha x cube minus 3x, 2 alpha x cube minus 3x minus x square by 2 dx. You have to do this. So what do we have here? 2 into 4 alpha to the power 6 by 9 pi square to the power 1 by 4, 0 to infinity. 2 alpha x to the power 4 minus 3x square e to the power minus alpha x square by 2 dx is nothing but 2 into, so this is common, so let us write this as k, k to the power 1 by 4 into 0 to infinity. We are going to get two things, 2 alpha x to the power 4 e to the power minus, acha, so minus x square by 2 minus x square by 2, we are going to get x square, so the power alpha x square, okay, and then we are going to get dx, and here we are going to get 2 into k to the power 1 by 4 into 3 0 to infinity x square e to the power minus alpha x square dx. Okay? So we are going to get 2k 1 by 4 as common, 2 alpha into, again range is 4, so we are going to get 4 minus 1 double factorial, 2 to the power 4 by 2 plus 1 alpha to the power 4 by 2, right? I am just using this when n is even. Alpha is equal to n by 2 into root over pi by alpha minus 3 into 2 minus 1 double factorial, which is nothing but 1 double factorial, n by 2 to the power 2 by 2 plus 1 alpha to the power 2 by 2 over pi by alpha. So this is I'm writing from 0 to infinity x to the power n e to the power minus alpha x square dx is n minus 1 double factorial I 2 to the power n by 2 plus 1 alpha to the power n by 2 to the power pi by alpha. Okay, so we can take 2k to the power 1 by 4 into pi by alpha outside. What we are getting 2 into alpha into 3 double factorial, which is nothing but 3 into 1, right? Divided by 2 into 2 plus 3, which is 8 alpha square. Okay, interesting. Alpha square minus 3 into 1 factorial double factorial is 1 by 2 to the power 2 is 4 alpha. So things are common. So alpha cut. So and 2 will get 4. So eventually we'll have 3 by 4 alpha minus we have 3 by 4 alpha minus 3 by 4 alpha, which is 0, right? So we got minus infinity to plus infinity psi 1 x psi 3x to be 0, that is when psi 1 and psi 3 are orthogonal. Similarly, here we got psi 0 and psi 2 are orthogonal. Using that odd function thing, we have also proved that psi 0, psi 1, psi 0, psi 3, psi 1, psi 2 are orthogonal. So this is one approach. For the odd function, you can do it very easily, right? So we can solve a few more questions, this 5.34 and 5.35 today, and we will solve some more question from hydrogen atom maybe on the next day. So let me solve a few questions here, at least one of the questions, so that you can do it in the next day, right? The 5.35 you can solve it yourself. So 5.34 and 5.34 are from rotational spectroscopy, which is a rigid rotor problem. So I hope you remember, right, that from the far infrared spectrum, the same molecule, there is a line separated by 2b. So you remember that in a rotational rigid rotor, the energy of the jet level is B into J plus 1 joules. J plus 1 level will be J plus 2 joules, right? So where B is a rotational constant and can be denoted as B is equal to h square by 8 pi square I. I is moment of inertia in joules unit. If someone wants to write it in centimeter unit, so then they have to divide it by hc and they will get 8 pi square IC centimeter inverse unit also. So the delta E, the energy gap between J plus 1 and J plus E is actually, you can see, you can take common J plus 2B J plus 1. So here you are going to see that under the energy gap between J and J plus 1 is 2B into J plus 1. Okay. Now, so you are going to get, so suppose the first line you will get at j equals to 0. Where are we going to get the point j equals to 0? The first, so delta E is associated with some hc by lambda, huh? Or hc nu bar. So for one j equals to 0, you are going to get one line in the spectrum. For j equals to 0, you are going to get it at 2b centimeter inverse, or 2b, whatever is the unit. Okay, so I'm not writing that unit because you know that you can get the unit of b in centimeter or in joules. Okay, so I can erase this part also. Anyway, yeah. What about j equals to 1? You are going to get another point, so that would be 4b. For j equals to 2, you are going to point at 6b. Okay, now for j equals to 3, you are going to get at 8b. So you can see the lines are actually separated. In the spectrum, the lines are actually separated by 2b. That is actually the interesting factor here. Suppose I am going to take j equals to 100. What is the thing which is going to come? 100 plus 1, 100, 200, 2b. What about j101, j99 maybe, 200b. And for this 102, 204b. See, even there also the gaps are 2b. Okay, so the lines separated by 2b. So that is what here it is given, that there is a series of lines separated by 16.72 centimeter inverse. So your 2b is actually 16.72 centimeter inverse. Okay. Now calculate the values of moment of inertia. From here you can see your moment of inertia is I is equal to h by 8 pi square bc in centimeter inverse. Whatever unit that is going to come, you can say. So we can write it down there, right? So I will be 6.626 into 10 to the power minus 34 joule second by 8 into 3.14 square into b is 2b. That means it is 8.36, right? Centimeter inverse into c into 10 to the power 10 centimeter second inverse. Centimeter inverse 1. Second inverse. Okay. I you are going to get, let me calculate from 6.626 into 10 to the power minus 34 divided by 8 divided by 3.14 square divided by 8.363, which is 3.39 into 10 to the minus 37 into 47 joule second square, which is nothing but kg meter again minus 2 second square, right? So we are going to get kg meter. Kg meters square actually. Am I making it correct? Let me check once. So joule is Newton meter. So your I is mu r square, yes. So it's correct. Kg meter square. Mu r square, mu is in kg and r can be written in terms of meter. So it's like that. So your I, your moment of inertia is this. Now you know your I is actually your mu r naught square, right? Because it's a rigid rotor. So mu we can calculate for 17h. So mu we have already calculated for these, right? Say h 79b or something like. Let us check. For this question, 1.64 into 10 to the minus 27. We have calculated 1.64 into 10 to the power minus 27 kgs. So you can get the values of R0 is root over I by mu, right? Which is nothing but root over 3.49 into 10 to the power minus 47 by 1.64 into 10 to the minus 27. Above is kg meter square and down below is kg, right? Kg gone, meter square will become meter. How many meters? That we need to see. That would be 10 to the power minus 20, which is 10 to the power 10, and here it will be root over 3.19 divided by 1.64 is 1.45. 1.45 angstrom or 145 picometer, something like that. Okay, so minus 10, I'm sorry. So the internuclear distance separation can be also be calculated, and also the moment of inertia. Similarly, for the next question, j equals to 0 to j equals to 1 transition. So for that, what do you need to do? J equals to j plus 1, so you know the energy is. So that transition is from j equals to 0 to j equals to 1 will be 2b into 0 plus 1, right? So from that you can calculate the h nu. It is also h nu, right? So your nu is given, your j is given, so you can calculate the value of b, the rotational constant, and from the rotational constant and from the mu of 12c and 16o you can calculate like this, something like this. You can calculate the bond length for the carbon monoxide, right? I hope you will be able to do that, and with that today I am going to stop the session, and I hope I will meet some of you on the next session and we'll discuss some more problem. From now I will totally go into the hydrogen atom and multi-electronic thing, right, as the discussion is going on in the lectures. So thank you for listening to me in YouTube. I hope, I guess. So I'm stopping here.